Hello, everyone, and welcome to our Fall 2022 webinar sponsored by Sectra. Our webinar will be 60 minutes today in duration, which includes Q&A. So I would like to start by respectfully acknowledging the land on which all of the OAP Board of Directors, faculty members, and Secretariat work, study, and live. We acknowledge our presence from coast to coast on the traditional territories of many Indigenous peoples, including the First Nations, Inuit, and Métis peoples. We strive for respectful relationships with all the peoples across our great country as we search for collective healing and true reconciliation and honor this beautiful land together. We share this acknowledgement with the intention to honor the past and contribute to advancing the Truth and Reconciliation Commission's calls to action as a step towards reconciliation. So hello everyone again, and on behalf of the OAP, I'm pleased to welcome you to Revolutionizing Pathology with Image Analysis and AI. Backed by popular demand, we are thrilled to have Sectra provide our members into a view of what they believe is needed for broader adoption of image analysis in clinical practice, and how they have chosen to work with customers and vendors in this field. The purpose is to describe concepts and not commercial solutions. We are thrilled to see participants from Ontario, across Canada, and also internationally. All are welcome. I recognize many of the names as prior attendees to our virtual education, and it's wonderful to have you back. You can access all of the recordings from all our events on the OAP website, and this link will be posted in the chat box. To keep things simple, all participants will be muted. If you have a question, please type it in the Q&A box. Questions may be answered during or at the end of the presentation. Participants can also upvote or comment on questions asked by participants. You can also participate by asking a verbal question, and you can do that by simply raising your virtual hand and we will unmute your mic. So we encourage you to learn with us, so use the chat box to share comments, experiences, links to reference material, or let us know how excited you are about the webinar today. We are all learning together. So it was wonderful to meet some of the Sectra team in person during the OAP annual meeting a few weeks ago and put some faces to names. Now with that today, I'm really pleased to introduce our guest speaker, Elin Kindberg. So Elin earned her MSc and PhD at Linköping University in Sweden with a focus on immune genetics and viral disease. After earning her PhD in 2010, she began working for Sectra, where she started as a medical advisor. She has led the journey of moving pathology from research to a commercial solution within the company and has been involved in digitization projects in pathology in Europe, Australia, and the US. I invite you to read her full biography in the chat box. Elin, the floor is yours.
Thank you very much. I hope you can hear me, and welcome again to this webinar where I will be focusing on revolutionizing pathology with image analysis and AI. So as said, my name is Elin Kindberg, and I work as Global Product Manager for Sectra's digital pathology solution. I've been working with this since about 10 years, and I've been involved in projects in Europe, Australia, Asia, and the US. And I am overall responsible for what we do within pathology at Sectra, what direction to take in development, what features we should build or what functions, and what technical platforms we support. And at Sectra, we develop a software solution for primary diagnostics of digital pathology, where we import images, we make them accessible to users based on permissions, enable efficient review of the images and reporting. But we don't develop our own image analysis. So instead, we enable others to integrate and make use of AI or image analysis from our software. And that's, of course, an important disclaimer here, because this is not meant to be a sales talk about what Sectra does, but more conceptual talk about how image analysis has the potential to make a big difference in digital pathology. And some of the examples that you will hear about, they come from Sectra's own user research, where we try to understand, so how could pathologists in the best way interact with AI? I have intentionally chosen not to include names of what vendors that we work with that provide different solutions, but of course, if you have special interest, you can ask about it. But my purpose is not to sell either our own or other AI solutions. But the topic, revolutionizing pathology with image analysis and AI, I mean, I'm confident that AI has the potential to revolutionize pathology, but there is still some way to go before the benefit is utilized in a broader sense. But I do feel that the movement that has started, we see that from the questions that we receive from our existing or potential users. And what I want to talk about today is why does image analysis has such great potential in digital pathology? I also want to talk to discuss some design considerations that should be made from the providers or from software providers like ourselves to help the uptake, to enable pathologists to use this and to be able to trust image analysis. I mean, this is new to all of us. I want to talk about some of the use cases where AI could be applied. I'm sure I won't cover all of them, but at least some areas. And as said, I mean, AI has not yet reached the broad clinical adoption. My experience, at least, is that usage is still very low, but we do know some things that are needed to change this, or that has the potential to change this. And finally, I want to describe the AI-powered digital pathology workflow that I envision in a few years that is already possible today, but we need to take the small steps and build the trust in AI to get it out there. So why image analysis in digital pathology? Where can it actually bring value, and what are the characteristics of deep learning? I mean, in the past years, in the recent years, research has shown that machine learning tools have the capacity to perform expert-level results in areas such as quantification or risk stratification, detection of malignancies, and so on. And the reasons why this has happened in the recent years includes advances in machine learning techniques with deep learning, and also the fact that more digital data is available and that this can actually be used for training the models that are to be used first in research and then in the clinical setting. I mean, without that digital data, you can't really train any algorithms. And the reason why pathology is well suited for AI, well, there are two primary reasons, I would say. First of all, it has the potential to improve the accuracy and reproducibility of diagnosis. And this is, of course, an area where there are known limitations today with a manual read. But it also has the potential to increase efficiency. And I mean, this is needed to address the global shortage of trained pathologists. And I'm not sure about data, how it looks in Canada, but I know for sure that in Sweden, we have a huge problem with lack of pathologists in most parts of the countries. And AI has the potential to improve the efficiency of pathologists in numerous ways, for example, by automatic pre-read of biopsies, detecting small lesions such as micrometastasis or microorganisms, for example. But there are a lot of areas where there is great potential. But there is a gap between what has been shown to work in controlled environments and research and what has reached clinical usage. We start to see the first pilots starting up, or the first real prospective use projects, but there is definitely a big gaps, and there are multiple reasons for this, and I will get back to this in a little while. But first, I just want to take a step back and talk about the terms AI and machine learning and deep learning. And this talk is not meant to dig into the technical details. I don't have a technical background myself, but on a high level, artificial intelligence can be described as software systems that demonstrate capabilities previously associated with a human intellect. And when we talk about image analysis and AI in digital pathology, then focus is typically in the sub-area machine learning, which includes deep learning. And while machine learning is based on the fact that the system will receive categorized features as training input, deep learning rely on training data being labeled as the target prediction, and then the model will by itself learn to extract the relevant features. And if you are like me, don't have a technical background, then this is a description that might help to differentiate between machine learning and deep learning. So here, in both these examples, where machine learning on the top and deep learning at the bottom, you have input data, which is a cat, and the purpose of training the model is to create an algorithm that can identify a cat. And if you're done working with machine learning, then you have this input data, and then you will have a domain expert who will identify the features that are tied to being a cat. So the fur, the 2 ears, the legs, tail, etc. And then thereafter, you will have a neural network that will train the algorithm based on this feature input. But when we talk about deep learning, then the algorithm will only get the input data of the cat images, and they are labeled as cat. And then it will train itself to learn why is this a cat? So what are the features that are identified as a cat? And this means that deep learning, there you have the potential to train also on things that can't be seen by the human eye, or that can't be identified by the human eye. So in machine learning, there is a limit to how good the algorithm can be, and that's like as good as a human or a little bit below that, while deep learning has greater potential. I hope that, like for me, this can help differentiate between machine learning and deep learning. So looking at machine learning, there are typically at least three typical characteristics. First of all, they can only be applied to specific problems. Secondly, they are so-called black box models. So you give them input, they do their calculation, and they will give you a result. But it's pretty hard to understand. So how did it actually come up with its result? And the third one is that more training data is better, at least if you have training data with reasonable quality. And here is why it's important, for example, with the fact that there is now more digital images and digital diagnostics done. So there is more training data to actually use when developing your algorithms. But starting with this fact that it can only be applied to specific problems. So as a pathologist, you have many different things on your desks, and here are some of them that we typically describe as examples. So you set the general diagnosis, you estimate the percentage of tubular structures, you dictate the report, you work with general improvements or do research, etc. And I'm sure you can add more to this. And all of these are definitely not well fitted for machine learning. Instead, it's just a subset of the tasks that probably are. And I mean, that's a good reason why no AI tool would ever replace the pathologist. But it definitely has the potential to let you focus on the task where the human brain is more powerful than the computer. So looking at these examples of things that you do, there are a few that are actually well fitted for machine learning tools. Counting mitosis, estimating membrane staining, counting number of positive nuclei, estimating percentage tubular structures, and doing or grading nuclei. When it comes to the black box part of things, it means, as I said, that you take an image in, for example, you do an analysis and provide a result, but typically doesn't describe how it came up with it. And based on this, but also to ensure that the user feels in control or can feel confident in the AI, especially at this point when AI has not yet reached this broad adoption, an important design consideration is what we call design for failure. I mean, we all know that all algorithms will fail under certain conditions, and that it's important that then it is obvious for the end user. So if the result is based on poor input data, you must be able to identify that this gives an incorrect result. And you've probably all seen these types of memes on the internet showing examples of, for example, dogs and bagels as to the left, or sheepdog or a mop. And these are examples where, as a human, we can have better capacity of determining what is obviously a dog here, but where the algorithms may do unacceptable mistakes. And to be able to utilize the capacity of AI without risking to label something as a bagel when it's actually a dog, the diagnostic solution must be designed for failure, as I said. And I will go through some examples of how that can be applied to different types of use cases. And this is now based on Sectra's user research, but I mean, it's generally applicable. So see these as examples. We did user research and try to identify, so how should the end user interact with the results in the viewer to ensure that they feel that if the solution has failed, then I will be able to identify that immediately. And I will start with the example of cell counting in a hotspot. So this is what a cell counting result could look like in an ideal situation. A properly stained slide, no folds, no dirt on the slide, with good focus all over. It's given an almost perfect result with only a few mistakes. I think there is some, so like a missed positive cell here, for example, maybe some missed negative cells as well. But I mean, this is almost perfect result, and it's probably can be accepted as it is. But we also all know that not all slides will look like this, and also relatively simple tasks from an AI algorithm's perspective is dependent on the input that is good enough. So here is a slide that where with what I believe is a focus artifact, leading to that the algorithm identifies cells that aren't actually cells. I'm not sure if the outcome would still be considered okay, but at least it is definitely not optimal. And then there will be cases where the algorithm has no chance of performing well, like this one. So what would be obvious to us as humans as being unspecific staining, the algorithm has in this case identified as Ki67 positive cells. And since it's easy for you as pathologists to see beyond the unspecific staining, these types of slides might pass the immune histo quality assurance, but it will lead to algorithms failing. And as long as it's easy for the reviewer to identify that the AI result is totally wrong, then this can be, I mean, it could be okay. You could just discard the automated result that you see here. And I mean, it would be possible for the provider of this AI tool to optimize the algorithm also for this type of artifacts or these images. But the problem is that the number of potential problems that could arise or that could affect the result of the AI calculation, that number is too large to be able to handle. And I mean, the issues that could arise are hard to predict to cover it all. So by designing for failure, you can help the user immediately identify when a bagel has been identified as a dog or when the background stain has been identified as a Ki67 positive cell. And I mean, you can compare these two types of visualization. To the left, you see a common way to visualize quantitated cells with an overlay. And then to the right, you see the way we found that it would be better to present the result, to ensure that the user could actually identify those cells that were incorrectly identified as positive or negative. And that to the right, that's an early prototype of a cell counting tool that we had. So overlays, I mean, there it's even if it's possible to make that transparent, it's easy for the end user to not identify when the algorithm did something that was totally wrong. So to the right, that's a pretty okay way to help the user identify those failed results, but it could be made even better. So one thing that you can do is to present the result as only one result type at a time. So here you only see the positive cells, making it easier to identify missed positive cells, like this one. You can do that very quickly, just looking at the image and see where the missed cells are, or vice versa. You can just display the negative cells. But here, with this type of visualization, it's pretty hard to identify what cells have actually been included in the algorithm. So therefore, we were looking at something called negative space to help the human eye to quickly identify missed negative cells. So here you can compare to this image, where all cells that are included has been outlined by a thin gray line. And then by just skimming quickly through the negative space, this will allow the end user to more quickly find cells which the algorithm has missed. And I won't try to identify those. I'm sure you can do it. So that was an example of how one can design a solution for a hotspot analysis, such as Ki67, where it's reasonable to actually look at all the cells that were included in the analysis. But what about larger areas or whole slide analysis? I mean, what we found was that there is like an upper limit at 2,000 cells, which is probably already that a bit high, when it's no longer possible for the end user to actually confirm all the analyzed cells. I mean, above 2,000 at least, then it's impossible to visually control the result. And depending on the regulatory classification of an algorithm, you may have to be able to verify the result. It depends on what class your algorithm will belong to. But if you need to verify the result, then you need to look for alternative solutions for how to present the result. So one thing that we looked into, mainly from a research perspective, was using stereology for doing whole slide analysis, and that could be applied to, for example, HER2 or PDL1. Stereology, I mean, it's an established method in medical research for estimating findings in larger areas, and it's based on the fact that instead of analyzing each individual cell, you will analyze a number of patches in the region of interest. And we looked at presenting the result in a so-called patch gallery, where the categories are that are available depend on the app that is used. So this is what it could look like. You choose your region of interest for a HER2, for example. In this case, the tumor area. You initialize the result, and I'm not sure if it's possible to see, but there are some dots here in the region of interest that are the chosen or the analyzed patches, and they are then categorized into different categories. Since this is HER2, they will be strong complete, weak moderate complete, weak incomplete, no stain, and excluded. And as an end user, you, instead of looking then at each of the cells in this region of interest, you just need to look at these patches and see if they are categorized correctly. Then that will be statistically significant or statistically correct as and generalizable for the whole region. In this case, if you click on a patch, then it would open up here to the right for better possibility to verify the result. And if you want to change something, you drag and drop in the patch gallery. Or use shortcuts. So, and then you can use these corrections for retraining of the algorithm. Another benefit with this model is that you can at very high speed verify the result. So if you just keep your eye focused on this cross in the middle, then it's possible to just step in between the patches and confirm the result. In this case, non-tumor patches identified in a region of interest. And then this way is a way to enable you as end user for a whole slide analysis to confirm the result and identify if the algorithm has totally failed for some reason. Trying to change the slide. Stereology with that grid with the number of patches, that's one use case where the patch gallery can make sense for visualization. Another one is mitosis counting, and this is an actual example of an AI algorithm that has been developed by researchers at Medical University of Utrecht in the Netherlands. So this is researcher or in-house developed algorithm that is actually in use at a digital pathology department. And they use this patch gallery for visualization. The end user will choose their mitosis algorithm. They will mark out the region of interest, and the algorithm will identify mitotic cells or possibly mitotic cells. As an end user, you will look through the patches and update the result. So changing mitotic cells to negative. Step through the mitotic cells, and when that's done, mark the result as verified. So this is AI that is being used at one site in Europe, at least. Another example of visualization for larger regions includes marking out the regions of interest, as has been done here, using different colors to indicate different findings. So like this tool for Gleason grading, where different grades are outlined in orange and dark red. So what is important when you do your design is that it should be obvious where things go wrong, using things like outlining the negative space, not using overlays, but instead just smaller indicators like the green cross and the red dot, or using these outlines with different colors, etc. And preferably, it should also be possible to change the result if something has gone wrong, keeping the end user in control, or at least to just discard the result as a whole. The third thing that was like a characteristics of machine learning is that more training data is better. You saw the example of the patch gallery where categories can be updated from positive to negative, for example, but also for the hotspot analysis, it should be possible to like change the positive to negative, etc. And then you can use these changes to retrain the model. And an important thing there is that it cannot be expected that things that are not updated are correct. You shouldn't use that as training data, but only expect that it's really when things has gone really wrong that the end user will actually make the effort to update. So one of the key things that has been identified for getting broader uptake of image analysis in the diagnostic routine is making it part of the regular workflow. So we see that when there needs to be a separate workflow for running the algorithm, then it won't happen. It will take too much time. But instead, it needs to be part of your diagnostic routine. And this is an example of how such a workflow could look like if integrated into the diagnostic workflow, based on our experience, but I'm sure it's generalizable to others as well. So an analysis can either be initiated manually by an end user clicking a button, for example, like with the examples that I showed, or it can run based on images being imported into your image management system. So with the automated system, as soon as an image is imported to your PACS or to your IMS, then that IMS can broadcast out to the image analysis solutions that are out there, saying, "Hey, I got this image. It's a prostate, H and E. Should this be analyzed?" And then the AI solution can respond and say, "Yes, give me the image, give me the metadata, run the algorithm, and send back a result." And then this can be done already before the image has actually been viewed by both quality assurance personnel or the pathologist. So based on metadata that is available in the image, such as body part, such as stain, maybe procedure, etc., the AI algorithm could know that this is an image that makes sense for me to analyze. Sorry for the animations. So there is no question about the fact that there are great possibilities coming with AI and digital pathology, but what are the more specific possibilities, and what use cases do we see that are now becoming regulatory cleared on at least some markets? Well, I found this image in an article that was written by David McClintock, who was at that time at least at the University of Michigan. And I think it's a good description of the broad span of use cases in AI in pathology. It spans from simple tasks that can be run on a client computer to more complex ones that will demand more compute power running on servers elsewhere. And it spans from analyzing digital slides pre-diagnostics, like with the automated workflow that I just described. This could be things like triaging cases by priority or flagging regions of interest, automatic quality assurance scans. I'm sure that's going to be like anybody's going to expect that in not too long. Pre-ordering immunohistostains and even predicting diagnosis. But then there are, of course, also things that should be done post the manual review. It can be, for example, things like risk stratification or mitotic counting or second reads, for example. But there really is a broad span of potential use areas for AI in pathology. And let me see if this works. I thought it would be interesting to see this image, which is like a theoretic example of where AI could be applied, and then see, so what about the vendors that we are working in? What use cases are they covering? So one is definitely triaging cases by priority. So first of all, I expect that everybody, as I said, will do automatic quality assurance prior to the image being read by a human being, and that it will be rejected with a reason if it doesn't look good. But then I see also triaging cases by priority. So prioritizing the cases that are identified as most probably malignant, flagging that in the work list. So either that should be read by a specialist, and these cases could be outsourced to telepathology, for example. Or this is something that I should read in the morning when I'm less tired, and these are the cases that I can read after that. Flagging regions of interest is definitely something that we see, where metastasis in lymph nodes is one of the very interesting use cases, I think. We see algorithms predicting diagnosis, both in prostate and in breast cancer. And finally, there is quite a lot of solutions for automating repetitive tasks, such as quantification of K67 or mitosis or hormone status, for example. So one of the most easy to grasp use cases for AI in pathology is quantification of positive cells in tissues, and probably the most common one that we see is quantifying ER, PR, HER2, and Ki67 for breast cancer. This has been the starting point for many of the commercial AI providers, at least looking back, and at the point where Sectra was considering of providing our own AI, this is also where we started, which is why we do have a legacy Ki67 in our software. And while there is no doubt that AI could provide good quantitative data here, my feeling is that one thing that has hindered the broad uptake of especially the breast panel AI is the business model versus the value. I mean, this is an AI panel that would preferably be pre-analyzed with a result pre-populating the report, but at the same time, as I've understood it at least, from our customers, the value of the algorithm is limited for many cases where already at a quick glance, you would actually be able to set the result yourself. So paying for usage only makes sense for some cases, while at the same time, it's preferred to pre-process the images already before scanning. So there needs to be like a cost-benefit balance there when it comes to how much are you actually willing to pay for this, while at the same time really getting the value of the efficiency gain, for example. So many vendors started, as I said, with the breast panel, and now we see other quantifications being rolled out, PDL1 quite common, and the P53, for example. And I'm sure this will grow as companion diagnostics is becoming more and more common, more drugs coming out. Lymph node analysis has been a task in many AI challenges that has been run, and there are many promising solutions that are coming. And this is a field where I personally believe that this could be one of the early solutions that could gain momentum in clinical practice. It definitely has the potential to show a positive return of investment. Typically a solution that could be set up and run as pre-processing based on body part, procedure, stain, and possibly something more. The algorithm can mark out the region of interest as has been done here. And like with the potential metastasis, and give information about the size, for example, to see what should be prioritized, and maybe more important, it could mark out where there are no findings, where there is no tumor. And this will, of course, be a challenge to trust the no tumor result. But if we reach that, there is great potential. Studies show that the potential time saving is 5 times. I'm not sure if that's reasonable. I'm sure, as said, it will take time until you trust that. But definitely, this is definitely going to be exciting to follow. There are quite a few examples of commercial providers who focused on prostate and prostate grading. This is the example I showed also before with the outlined areas in different colors that should hopefully help you identify and confirm the result. This can be pre-run based on prostate, obviously, and the stain. It will identify areas of interest. It can report the Gleason grading and the group, and this could auto-populate a result as well for you to confirm or verify. This is an example of a use case for AI where it offers potential to provide information that is not possible to extract with a human eye. So based on an H&E stain, there are applications that can determine the expression of proteins such as ER, PR, and HER2. These are regulatory cleared in Europe, at least. I'm not sure how it is in Canada, but it has, of course, great potential both when it comes to being cost saving, because there may no longer be a demand for doing the immunohistochemistry stains, but also to decrease the number of slides that should be read and shortening the reading times. Another example of where AI has potential to find more than the human eye is stratification among cancer patients. So we've been working with 2 companies in this area that use H&E stains to stratify between patients with breast cancer and colorectal cancer and their severity of disease. So the first one, the graph shown to the left, is focused on breast cancer and specifically at patients graded at Nottingham grade 2. Which I've understood, if that's correct, that more than 50% of all cancers are. And today, I mean, the clinical decision is, of course, often dependent on expensive molecular assays that may not even be accessible at all hospitals. But then using this algorithm for stratifying the Nottingham grade 2 patients into high and low risk, there is potential to decrease the over and under treatment of patients with early breast cancer. And of course, it has potential to both save time compared to sending these samples to molecular analysis, and also at those places where that's not available, it has potential to add more information simply. And similar to that algorithm, to the right, there are graphs for colorectal cancer that stratifies patients into the ones with a good versus poor prognosis based on analysis of the resected colon tumor. And again, just giving more information to help ensure that you under and over treat less patients and just get a better patient outcome overall. So these are also solutions that are already available, at least in Europe. So those were a few examples of things that we see are now reaching they're possible to run clinically, but we are still waiting for that big boom when it comes to AI in the diagnostic world. But those were like analysis of the images. And then the next step is, of course, to use this result to triaging cases, or as mentioned before, starting with the most important one, or according to a flag pre-run AI, etc. So definitely the AI has the potential to affect your workflow and ensure you focus on the right thing at the right time. And also there is a possibility to use AI to do double reading, like has been done in mammography for a long time. So flagging things where the human read and the AI disagrees simply. When it comes to auto-populating reports, it includes anything from a suggested diagnosis, the grading information, or the result from the quantification. And this could, of course, based on the result, that could, using standard communication protocols that are available for medical IT systems, this could already be sent via so-called HL7, for example. So great potential, a lot of good stuff coming out, both in research and when looking at the regulatory approved solutions that are out there already. But as said, the revolution has not taken place yet in clinical use, and there are multiple reasons, I would say, to why it hasn't reached those high levels in clinical practice, and some of these are easier than others to approach. One reason is that digitization in itself it's only now taking off, I would say, to broader in any broader sense. And without the digital workflows, there is limited opportunity to take advantage of the AI. But now we see that digitization is taking off. I understand that also in Canada there is a good push for digitizing. So there is definitely hope. Another reason is the lack of standardization. Many AI models have a limitation in the file formats that has been used for training the model, and therefore it's not compatible with all the file formats that are being used in practice. And they often, unfortunately, they have lacked DICOM images as input for their training. But again, standardization is happening, it's taking off, so this issue should decline. The there has been an unclear business model. I mentioned the fact that I mean, the benefit may only be for a few cases, but at the same time, you want to run as much as possible with automated pre-analysis to save time. So there is like a question, should it be a subscription model? Should you pay per use? And what is the reasonable price points where labs can pay and the companies can at the same time earn money to continue to develop solutions and support customers? And fourth, but probably not the final factor, is the lack of truth from prospective studies. Most evidence that this has great potential comes either from retrospective studies or on curated or research data, or small prospective studies with limited size. And for broad adoption, there is a need to get evidence from real world usage, and you want to hear people use it in reality before you trust it. So I found an article, an interesting article by Steiner and colleagues that talk about closing the so-called translational gap for AI applications in digital pathology. And there was this pedagogical figure showing two parallel workflows, one for AI development in pathology, which you see here, with like you choose your problem, you curate your data and develop the machine learning algorithm, you do the validation and you do some UX evaluation validation. And then the other workflow, the digital pathology workflow that includes regulatory approval, integrating the model into the clinical routine, typically first for a controlled specific use case and then expanding it more broadly. I mean, this is where we are at its best at this point. So after this, there is a need for prospective validation of AI solutions in digital pathology, and then further development and monitoring about performance and building the real world truth or proof, I should say. So we start to see this. Happening, and I think this is gonna, once it gains momentum, it's going to be easier. It's going to be a no-brainer to implement AI as part of your regular workflow. So I think if you are considering AI, and I mean I hope and assume that most of you do, I think that it's important to take things into like the right order. You need to start with the lab process. If you're not already digital, to adapt your lab to a digital workflow. Start scanning so that you can scan everything, do the digital readouts routine in your practice, integrate the AI, and then think about, so how should we configure our workflow to ensure that we benefit this as much as possible. But what if we looking at when the revolution has happened? So how could that actually look? So first of all, I mean, as I said before, I think that automatic quality assurance, that's going to happen everywhere. And then as soon as an image comes into the image management system, in this case, we pretend it's a breast case. It will broadcast to the surrounding image analysis solutions that, hey, I got this breast case. There is a lymph node. It's a breast. It has the full panel, and also, as I said, the lymph node stained with H&E. The application from one vendor will pick up the lymph node and do a pre-analysis, flag cases as no tumor or there are actually metastasis, and another one will process the breast panel and do mitotic count, etc. It will be visualized in a way that the pathologist can confirm that the analysis result looks reasonable. I mean, no bagels identified as dogs, and you can correct the mistakes. It could also be expected that an algorithm will detect things as cancer or not cancer, and if the case is identified as a Nottingham grade 2, then it could be pre-run with a risk stratification algorithm that I described earlier. So we have the broadcasting goes out, the images are sent, the algorithm is run, the result is sent back and visualized simply. And this is available already as the case reaches you for primary diagnostics. So together, it has the potential to prioritize cases with high probability of being malignant, identify the metastatic cancers, indicate protein expression, and speed up your reporting. No way that it's going to replace pathologists, but it can definitely revolutionize the space by increasing efficiency and quality, and it has the capacity to do really, really big things, but it's still some time away. And my experience is that, I mean, it's easy to look for what is needed from a development perspective to get AI going, but I'm a strong believer of that what is needed is to start using what is already available, and that usage is what's going to teach us. So what are the real demands when it comes to better integrations or alternative user interaction tools? So small steps are being taken. We see the projects are being requested to start, or that they have already started, and I'm confident that the movement has started, that in a few years a talk like this can be filled with more real-world benefits of usage in prospective ways, and less potential areas where AI can revolutionize the field of digital pathology. So thanks for listening, and I look forward to hearing what questions you may have.
Thank you so much, Elin, for showing us some of the potential of digital pathology and AI. I'm sure many of us listening can see potential use cases in our own pathology practice. So I would just like to take some time now to answer questions. We also have David Boissonneau from Sectra here to help facilitate that. So please feel free to put some questions in the Q&A.
Currently, there are no questions in there, so.
Okay, well, maybe I have a question to get things started. So, you know, in working with different labs, have you seen examples of successful business cases for starting digital pathology and AI? That's something I know that we've struggled with, is just making that initial business case.
I've seen it, not for AI specifically. I think we're still waiting for that, but we've definitely seen it for digital pathology, especially when you work in like a regional setting where you work with where multiple labs that want to collaborate and want to create more of a virtual lab that covers, or virtual department that the workload balance. There we've seen that the decrease of logistics around sending cases physically in between the sites, and also the possibility to better utilize the workforce simply. That's where a lot of the return of investment lies. So less overtime, for example.
Yeah, I think I think certainly it's an easier case to make in a regional sort of situation, or a multi-site institution. That's for sure. I think, you know, one of the things that's very different, obviously, between pathology and medical imaging is we still need to make the glass slide, whereas digital imaging was able to, you know, get rid of their hard copy films and their film libraries.
Yeah, I think a strong driver in many labs that we've been working with is the quality increase, and the decrease quality increase, and the decrease of, for example, human errors when it comes to, I mean, mixing up the case simply, things like that, and lost glass slides, etc.
We do have one question that was put in there saying, what is the minimum budgetary commitment to enable the use case scenarios you mentioned, like scanner, IT, etc.?
Oh, that's a good question, which I unfortunately cannot, I don't know, to be honest.
Yeah, I guess it would depend on a lot of factors, including case volume and the specific use scenario. And I think, one thing that I think your presentation really brought home is, without digital pathology, there really is no AI, and
Yeah.
That's really the first step. So, I think a lot of us look at this, we see that potential. But we still have to get over that first step in our institutions of going digital.
Yeah, no, I fully agree. I mean, the AI was, looking back a few years, it sounded like one talked like AI will drive the digitization. But as you say, without the digital workflow, it really doesn't increase the efficiency. So, and there are no digital images to analyze. So,
looks like we have another question. Do you think that digital storage limitations continue to be a barrier to adopting AI and digital pathology as a whole?
No, I mean, maybe for training purposes. So if we look at storage, and now I can of course only talk about our experience from Sectra. I mean, if you talk about archived images for training, then yes, because we sometimes see that not all images will be stored forever, even though many of our users do store their images forever. But if you talk about using AI more from a perspective, then no. But for training purposes, yes, then storage cost could be a limiting factor in case fewer labs are actually storing images long term.
And then we do have another one that says, are the Sectra scan slides open source? That is open to development by all enterprise users, or is development of AI algorithms limited to Sectra selected third parties only?
So first of all, we don't develop any AI our own. So I mean, so what we do, we have an open API that allows for anybody to integrate really. And as an end user, or if you're a customer, then you can develop your own research algorithm and integrate it simply into your workflow. If we're talking about the slides, we import the images as are. We don't change them. They won't be any Sectra format. They will be the SVS or the NDPI or the DICOM that we got them in as. Not sure if that answered the question.
And then we have another saying, do regional digital pathology image repositories have benefit for AI usage rather than individual site storage?
I would say it's a similar benefit to both of them.
And that prior question you answered said, yes, that is the question. Thank you. And then one other one here. Have you been able to solve the problem related to Z-stacking in digital images, especially in reference to cytology or hematology slides?
So if it depends on what the problem expected is. I mean, again, talking about our solution, we have support for the Z stacking, like reviewing the images as a small stack. I would say that the main issue when it comes to cytology or hematology images is the size of the images. I think that the scanners they're speeding up. They are becoming fast enough to actually scan in multiple focus layers, but they create a lot of data. So if we're talking about a lot of data in histopathology, then storing hematology for longer periods will be challenging for IT budget.
There are no other open questions.
But it's possible from a technical perspective, more budgetary discussions, I guess.
Okay, well, we're pretty much on the hour now, and so I just want to say a huge thank you to Elin and to David and to the Sectra team for a very engaging presentation, and in an evolving field that continues to be of great interest to pathologists. And I want to thank all of our participants very much. And I encourage everybody to participate in the short evaluation that will follow this session. I think there's a link in the chat. And it will help us to continue to offer valuable educational resources to our members. And also for those of you who are practicing Ontario pathologists or residents, just a little plug to renew your membership or to consider joining the OAP so that we can continue to have the resources to support you, our members. Thanks again, everyone, and have a wonderful afternoon.
Thank you.